Hey everyone, welcome to InsightsByRish. In today's video, we will try to build a human face generator system using GAN, and especially we are going to use a variation of GAN which is DCGAN, and that stands for Deep Convolutional Generative Adversarial Network. So here what we are going to do is we are going to feed our model a set of human faces. Like, it will be the training data for us. It will consist of many human faces of different caste, creed, race, and even nationality, and these all images of human faces will be fed to our model, which will result into some random face generation as an output. So this is the dataset that we are going to use, which is Flickr faces dataset resized, and in this dataset we have three types of images. Firstly, we have 128 by 128 image size. Secondly, we have 256 by 256 image size, and lastly we have 64 by 64 image size. We are going to primarily work with 64 by 64 image size because each directory consists of, I think, around 50,000 images, and hence if you try to work with 128 by 128 dimension or 256 by 256 dimension, then in that case your system crashes because it runs out of current memory. The GPU provided to you by Google Collaboratory or Kaggle is limited, and hence if you try to overload it with a lot of data, it gets crashed. And hence we are going to work with 64 by 64 images. Now the 64 by 64 images are themselves a bit of blur, or we can say noisy, and hence the generated images will also consist of noise. If you want to generate very high resolution images, then you have to work with 256 by 256 image size, which is not possible in our systems, and hence we are going to work with 64 by 64. Now, starting with, I will be implementing this project on Kaggle itself with the help of GPU provided by Kaggle to us. So here I will click on new notebook, which will redirect me to a new notebook page. So you can see that this is the notebook page in which I will be writing the code, and here on the right hand side we have some important aspects of this notebook, which is the dataset that we are working with, the output that will be generated by us, and even whatever table of contents that we will write here will be present here. Then scrolling down, here we have some session options, and here we are going to select GPU T4x2 for working with such images. These are the three types of accelerators made available to us: GPU T4x2, GPU P100, and the TPU. We are primarily going to work with GPU T4x2, which is kind of powerful. So let me click on that, and as you can see, we have a limited availability of GPU, like 30 hours per week, from which 4 hours I have already utilized trying this, and now we have 26 hours left. So in a week you can utilize GPU for around 30 hours, and after every week the limit will reset. So let me just turn on my GPU. Now, after connecting to the GPU, we have to start this session by clicking here on the start session option. So the session is starting, and this is just a demo cell given to us. We don't require this. Let me delete this. Let me name this notebook actually human face generation, and we are going to implement this using DCGAN. So this is our final interface, and we are going to start working here now. So starting with some basic introduction about DCGAN. It's a variation, or we can say an extension of GAN, and it basically has two important parameters, or we can say two important aspects. So the one is generator and the other one is discriminator. Both works against each other, and I will emphasize on the thing that both generator and discriminator are a kind of neural networks, like both are multilayer perceptrons. A generator is one which will try to produce random images out of the training data distribution, and the discriminator is the one who will try to identify that which one is fake and which one is real. By that, what I mean is, discriminator will basically try to identify whether the image that came to discriminator model has arrived from the original data distribution, that is, whether it is real, or it has arrived from the generator images which are generated by the generator. So this is how the discriminator will learn to tell the difference apart between the original images and the images generated by the generator, which are fake. So with every training layer, the discriminator will evolve to identify more and more minute differences in the original and the generated images, and with every improvement of discriminator, the generator will also improve to produce more and more realistic images. So this is how both are going to work against each other and still produce an output that will benefit us. And also, we don't want to build a strong discriminator here. We want to build a lenient discriminator, because if the discriminator is way too powerful, then it supplies very less confidence scores to generator, which will result into generator not learning anything from training data. Hence, we will make a powerful generator but a lenient discriminator. So let's start implementation, and I will also provide this code file here. In this code file, I have actually written every theoretical concept about the implementation that we are doing, including the steps and why we require some parameters and what's the significance of every method here. So I will provide this in the description box. Do check that. So let's start the implementation here. Let me give the title here, which is Human Face Generation using DCGAN. So the first part of this project is loading and pre-processing the data. So let me write here loading and pre-processing the data. So in the first cell, we will start importing libraries. So let me write it, import libraries. Here we will import all libraries as per our requirement whenever we need them. And let me also import warnings here. So import warnings. And I will ignore them. Now first, here we have to specify our data directory, which you can also say it as paste directory, from where we are going to extract the data, and we have to provide the path to that directory here. So let me just write here data directory, and in this data directory we have to provide the path. Now here we have our data sets. As you can see, this is the input portion in which we have our data set. Let me maximize it. And here we have the three folders of the different image sizes. We are going to work with 64 by 64, and in that we again have a faces directory in which we have our images. So as you can see, these are all our images. So we have to copy the path to this faces directory, and let me copy it and paste it here. So this is our base path. Let's run that. Now here in the next cell, we have to set some image parameters. So let me write set image parameters. Now here we will be setting some key parameters of our images. The first parameter here is image size. Now as I said previously, the images are already 64 by 64, but we won't take any risk. We will again explicitly try to make them into 64 by 64 dimension. So let me write here 64 as the image size. Then the buffer size. So buffer size is required when we are shuffling the data. This is the maximum limit in which the shuffled images can be generated. So let's give this limit as 50,000, which means the shuffled images cannot be more than 50,000. And then the batch size. So batch size is basically that we are passing the images to our model in some batches and not individually. So let me give the batch size as 200. These are all the hyperparameters. You can play with them. So let's run that. So this was the data loading stage. Now we are going ahead with the data pre-processing stage. So let me just show you this file as a reference here. Here I have written all the theoretical part. So this is the data pre-processing that we are going to do primarily. First we will access the images from the directory. Then we will explicitly convert them into RGB. Though they are already in RGB, still we will explicitly convert them to make sure that none of the images are in grayscale format. Then we will resize them, as we have already given the image size as 64. Then we will convert their data type explicitly to float, because the resized images need to be converted to float data type. And then we will normalize the data between the range -1 to 1. In typical machine learning or deep learning models, we normalize the data between 0 to 1, but while working with GANs, we will normalize the data between -1 to 1. And this is because the GANs really work very well when the data is distributed to a symmetrical range around 0, as it helps them to effectively train more and more better. And after normalizing the data, we will append all the pre-processed images in the folder. So this is how our data pre-processing will look like. So let's start coding now. So coming back to the notebook here let me write data pre-processing. So here let's write the function for the same. Here I will say def load images. This will be the function which will help us to load the images and also pre-process them. Here we will pass a directory, which is the path for the directory. Just a minute. And after that we will pass the image size here. So image size. Now coming in this function, first we will create an empty folder in which we will append our preprocessed data, which is this. So in this images folder we will be appending our preprocessed data. So here we will say for subdirectory comma files in os.walk directory. So basically why we are using this method is it helps us to traverse all the files in the directory without any issue. So even if it encounter a folder inside this faces directory, it will skip that. I have written everything about the importance of this method here. Fine. So you can refer this GitHub repository for implementation purpose. Now coming back, here I will say for file in files. Here I will say step 1. So step 1 is basically accessing the images from the base directory. So here I will say file path is equal to os.path.join. Now what are we joining? We are basically joining the subdirectory that we have here with the file name. So we will access every individual file name from the base directory and we will append that with the directory. If in case we have the subdirectory, then in this variable we will be having the subdirectory name, and if we don't have any subdirectory, then the original base directory name will be passed here, and then we will join it. Now after joining that, here let's write a try catch block. Inside this try catch we will pre-process our data. So the next step is step 2. And the step 2 is converting the image explicitly into RGB format. So here I will say image is equal to image. Now we require this image model from PIL. So let me go to the initial cell and here I will say from PIL import image. Let's run that. And coming back to this cell, here I will say image.open. So we are opening this image present on this file path. Let me just paste it here. And after opening, we are converting it with the help of inbuilt convert method into RGB format. So this is how you explicitly convert an image. After performing this step 2, the next step that we have here is step 3. So let me write step 3, which is resizing the image. So here I will say image is equal to image.resize. And for resizing, we will pass this image size twice, like image size comma image size. So let me just copy it here and paste it here. So this will resize our image explicitly into 64 by 64 format. After that, we will perform the step 4. The step 4 is to explicitly convert the image data into float format. Now for this we require numpy. So let me also import that here. Here I will say import numpy as np. Let's run that. And coming back to this cell, here I will say image array is equal to numpy.array. In this numpy.array, we will pass this image and we will make use of asType method which help us for data conversion, and here we will say float 32. You can just say float as well, but I will be explicitly giving float 32 as size because there are two variations of float 16 and float 32. I want it to be specifically in float 32. And after that, here we will say step 5. Now step 5 is of data normalization. So here I will say image array again. Now as I said previously, for GAN we are going to normalize our data between the range -1 to 1, as it should be symmetrical around 0, and hence here I will say image array minus 127.5 and again divided by 127.5. This will help us to normalize each and every data between a range of -1 to 1. Now after normalizing the data, we will perform the step 6, which is our last step, and that is appending all this preprocessed data in the images folder. So here I will say images.append the image array. Now we will come out of this try block and here I will say except exception as E, and we won't write anything in this except block. We will just pass it, and then here we will return our data. So return np.array images. So after putting all the preprocessed images in the images folder, again we will return this images data in the numpy array format. Now coming out of that function, let us call that function here. So here I will say images data, and here I will call the function of load images. Actually the function name should be load and preprocess images, so let me just make it that way because it is doing both the things. And then I will call this function here. In this we will pass our data directory, which is our base path, and then we will pass our image size. Let's run that. So we haven't imported the OS module yet, so let me also import that here. Import OS. Now it will work fine. And also one more thing, that this return should be in indentation with the first for loop. So let me just bring it back because it should be outside the inner for loop. So the indentation of the outer for loop and the return should match. Fine. Let's start running that. And the running has been started. It will take a good amount of time to load the data and even pre-process it. So now after the completion of this cell, let us check the length of images data here. So as you can see, in total we have 52,000 images, and you can even check the image dimension here. So let me just say images data, which consists of all images. I will only display the first one here. Let's run that. And as you can see, these are the values of the first image present in this images data, which are normalized between -1 to 1, and you can even check the shape of that here. So it is 64 by 64 and the channel dimension is 3, which means the images are in RGB format. If the channel dimension is 1, that means the images will be in the grayscale format. Now after doing this, we have to do one more thing in the pre-processing step, which is shuffling the data and also converting it into a batch. First we have to convert the images to a Tensorflow dataset, and after doing that we have to shuffle and batch the dataset. Shuffling is important because it helps the model prevent learning the data as per the order. Many times it happens that the model learns the training data as per the order it is present in. So we don't want that. We don't want that the model should learn the data as per the order. We want that randomly it should learn the patterns from the images, and hence the shuffling helps us in that. So here I will say batch and shuffle the data. So let me just say here train dataset, which will consist of our batch dataset, and here we will say TF. Now we require TensorFlow as well, so let me import that first. Here I will say import TensorFlow as TF. So coming back to this cell, here I will say tf.data.dataset, and here we will make a use of from tensor slices method, which is inbuilt in TensorFlow. So from tensor slices, this will help us to convert the images to a TensorFlow dataset, and in this we will pass our images data. So this code will help us to convert the images that we have in this images data into TensorFlow, and after converting that, then we will shuffle it. So shuffle, and in shuffle we have to give the buffer size, like the shuffled images shouldn't be greater than the 50,000 length, as we have given buffer size 50,000. So the shuffled images shouldn't be greater than this buffer size. So let me put it here, and after shuffling then we will create a batch dataset here. So let me just say here batch, and in this we will pass the batch size. So we are creating a batch of 200 images each. You can play with the batch size, that's a hyperparameter, but I will be keeping my batch size as 200. So let's run that, and let's check the type of this train dataset here. So type of train dataset. So as you can see, it's a batch dataset from TensorFlow. This is what we wanted to do. So that's the end to the first stage of the project, which is loading the data and pre-processing it. Now we will move ahead to the second stage of this project, which is visualizing the dataset. So let me write here second stage, which is visualizing the dataset. Now to visualize the dataset, we will require matplotlib. Hence, let me import that first here. So import matplotlib.pyplot as plt. Let's run that. Now coming back to this cell, let's write the code here to visualize first 3 images. So here I will say image files, and in this image files we will make use of OS list directory method. So list directory, data directory will pass our base directory here, and this will help us access all the images from the data directory, but we just want first 3 images, and hence I will say here first 3. Now after doing that, here we will create a subplot. So create a subplot because we want to visualize first 3 images simultaneously. So here I will say figure comma axis is equal to plt.subplot, and here we will say 1 comma 3, that is 1 row and 3 columns. In a single row we want 3 columns, and then we have to give the figure size here. So figure size is 15,5. Now after creating this subplot, we actually want to plot our images in this. So let's write a for loop for this. Here I will say for I comma image file in enumerate image files. So this image files, which consists of our image data that we will pass here, and I will be the index that will be tracking the images, and image file will have this data. So here I will say image path is equal to os.path.join, and we will be joining our data directory, which is our base directory, with the image file. Now after joining that, here we will open the image file. So let me write open the image file, and to open this we will make use of image module that we have imported from PIL. So here I will say image is equal to image.open, and here we have to pass this image path. Now we will display the image. So let me write display the image, and here we will say axis at i.imShow. This will help us to show the image, and we will pass this image here. And we also have to switch off the axis because we don't want anything on our x-axis or y-axis, and hence here I will say axis off. So that's the end of for loop. Now coming out of this for loop, here I will say plt.tight_layout. This will help us to properly display all the 3 images in a single row without any overlapping, and let's run that. So as you can see, these are the first 3 images from our data directory, and as you can see, they themselves are very noisy. So hence our generated output will also consist of noise. Now these images are noisy because we are using 64 by 64 dimension of them. If we work with 256 by 256 or at least 128 by 128, that will give us a more clearer picture, but we can't do that, as I said, the limitations of RAM. So after visualizing this data, now we will move ahead to the main core part of this project, which is creating the models, generator and discriminator. We want to create these 2 multi-layer perceptrons individually. So coming back to this next cell, here I will just write the heading, which is creating the models. The models that we are creating are generator and discriminator. Let's run that. So first we will create the generator here. So let me write generator, and after creating the generator, then we will go ahead for discriminator. Now before building this generator, let me just show you some technical aspects of that. As you can see here, this will be the 3 important components of our generator. First we will have some dense layers for the input, then we will generate a latent vector, then we will have some transposed convolutions for upsampling, and then we will have a final layer. I won't go much deeper into the theoretical concepts because this video is about implementations, but some basic things are that we will have a spatial dimension of 8 by 8, then we will have the channel depth as 512. This will result into our latent vector of 8 by 8 512. Then we will perform transposed convolutions using convolutional 2D transpose inbuilt method from Tensorflow to upsample the data. So initially we will have 256 channels, then 128 channels, and then 64 channels. and then we will produce a final layer that will generate an output of 64 by 64 dimension with 3 as the channel dimension. And in the generator part, we will be making use of ReLU activation function for all the layers except for the output layer, which will consist of tanh activation function, because in any GAN, the output layer of the generator should have tanh as their activation function. So let's start implementing that. Going back to the notebook, here I will first explicitly define the latent dimension as 100. If you increase this latent dimension, it will help us to produce more variable results, and if you decrease this latent dimension, it will help you to produce less variable results. So we aren't producing highly variable results, nor we are producing very less variable results. We want it somewhere between, balanced, and hence the latent dimension that we will give is 100. So let's write a function here of generator. Let's name this function as generator model. Now coming inside this function, we will make use of keras here. So let me just say model is equal to tf.keras, because keras is present inside TensorFlow module, and we will build a sequential keras module here. So let me just say sequential. Now first we will have our dense layer of random noise. So let me just say here dense layer of random noise. So let's build that dense layer here. So I will say tf.keras dot layers dot dense, and as I said previously, we will have a spatial dimension of 8 into 8 into 512. After that, we will give the input dimension here. So input dimension is equal to, this will be equal to the latent dimension that we have, and then we will have the activation function here, which will be ReLU. This will be ReLU only for generator. In the discriminator part, we will make use of leaky ReLU activation function. After that, we also have to add one batch normalization layer. So here I will say tf.keras.layers.batch normalization. So this was the first part of building the dense layer of random noise. Secondly, we want to convert this 1D layer to the 3D. So here I will just say converting 1D to 3D. This is actually the second part, so let me name it accordingly. Now coming back here, I will again say tf.keras.layers.reshape. Now in this reshape, we again have to give the spatial dimension of 8, 8 and 512. After this, we will build our first transposed convolution upsampled layer basically. So here I will say first transposed convolution. So let me just again say here tf.keras.layers. Now we will make use of convolutional 2D transpose here. So convolution, and as you can see here, we have this convolutional 2D transpose here. Let's select that. Now in this, we first have to select the filters, how many filters we want. We will start with 256 filters here. After that, we have to give the kernel size. So the kernel size will be 4 by 4. Again, this kernel size is your hyperparameters, and even the filters are the hyperparameters. You can play with that. Now after that, we have to give the strides here. So strides, we will keep it as 2,2. Then we have to say padding is equal to same, and then we again have to mention the activation function here, which is ReLU. After that, we again have to add the batch normalization layer. So let me just copy it from here. So this was your first transposed convolution layer. Similarly, you have to build 2 more transposed convolution layers, and after that you will have your final output layer. So let me just copy this and paste it here. This will be our second transposed convolution, and this will be our third transposed convolution. In the first, we will have 256 filters. In the second, we will have 128 filters. And in the third, we will have 64 filters. Everything else will remain same. After this, we will come to our final layer, which will be our output layer here. So let me just say here final layer, and here I will say tf.keras.layers. So this will be a plain convolution 2D layer. This won't be any transposed one, and in this we have to again pass the output. So as we are working with color images which are in RGB format, we will be passing the channel dimension 3 here. This 3 represents the RGB channel dimension. After that, we again have to give the kernel size, which will again be 4 by 4. And then again padding is equal to same. And in the final output layer of the generator, we will make use of tanh activation function. So activation is tanh. Now here we won't be having any batch normalization layer. So this is our model and we will return it after that. So return model. So this is the generator model function which will help us to build a generator which is a multi-layer perceptron that will consist of transposed convolution layers with ReLU activation function, and in the output layer we will have tanh activation function. And as we are working with color images, the channel dimension 3 has been supplied here. In the same cell itself, I will call this function in the variable generator. So generator is equal to generator model. And before running this cell, don't forget to give one more parenthesis inside this reshape. Fine. So after doing that, we can run it. So now we can check the generator summary here. So let me just say generator dot summary. Let's run that. And this is your generator summary. As you can see, we have one dense layer, then the batch normalization layer, then the reshape layer. Then we have various 2D transpose layers of convolutions. And then we have one final output layer, which is producing an output of dimension 64 by 64 by 3. 64 by 64 is your image size and 3 is your channel dimension. So this was the generator part. Now we will go ahead for the discriminator part. So let me just name it as discriminator. And let's run that. Now going to discriminator part, even discriminator is a multi-layer perceptron. It's basically a neural network similar to that of generator, just it has a different objective. So we can say that the discriminator is a CNN based image classifier that helps us to identify between real image and the fake image. So let's start writing the code now. First we have to specify the input shape. Now, as you know, we are working with 64 by 64 images, hence our input shape will be 64 by 64 and the channel dimension will be 3. Now let's write a function similar to that of generator here. So we will say this as discriminator model. And in this function, we will specify our discriminator model. So here we will say model is equal to, again we have to build a sequential keras. So tf.keras.sequential. Now in this sequential keras of discriminator, we just have to reverse the layers that we had in generator. So as you can see in the generator, we first had a layer of 256 filters, then 128 filters and then 64 filters. Here in discriminator, we have to reverse this order. First we will have a layer of 64 filters, second we will have a layer of 128 filters, and lastly we will have a layer of 256 filters. So let's start building that. First here I will say first convolution 2D. Here we won't be making use of convolutional 2D transpose layer. We will just make use of plain converse 2D layer. So here I will say tf.keras.layers and let me say convolution 2D. So this is the layer that we are going to use. Here we will pass the number of filters. We will say 64. Then the kernel size, let the kernel size be 4 by 4. Then the strides. So strides are 2 by 2. Then padding is equal to same. Then input shape. Now input shape will be equal to the input shape that we specified here explicitly. Let me just paste it here. So this is the first convolution 2D layer that we will have in our discriminator model. Now if you pay close attention to the layers, you can see that in the generator layer I mentioned this filters and kernel sizes attribute names explicitly, whereas in the discriminator I didn't do that. And both these neural networks will work completely fine because it is up to you. If you want to give that attribute names explicitly, you can do that, and if you don't want to, you can still go ahead with that. I tried to display you both the methods here. Now moving ahead, you might also notice one thing, that in the generator we had an activation function here, but in the discriminator we haven't specified it yet, and this is because here we are adding leaky ReLU activation function, and the leaky ReLU activation function needs to be added explicitly after the batch normalization layer. So first let me add the batch normalization layer here, and after adding this batch normalization layer, now I will add the leaky ReLU activation function. I will say tf.keras.layers, and I will add a leaky ReLU layer here. So leaky ReLU. So this was the first convolution 2D along with the batch normalization and the leaky ReLU layer. In similar fashion, we will add 2 more layers. So let me just copy it and paste it twice. So this will be our second convolution 2D layer, and this will be our third convolution 2D layer. In the first layer we had 64 filters, in the second layer we will have 128 filters, and the last layer of 256. Fine. So this is how the discriminator model will look like. It's just the reverse of generator. And you might notice that we haven't added a layer of 512 filters here. You can even do that, but that will make your discriminator more powerful, which will eventually affect the output of your generator, and hence we have made a lenient discriminator here, as I said in the beginning of video. Now after this we want to add a flattening layer and the dropout layer. So let me just say here, fourth thing is flatten layer and dropout layer. So here I will again say tf.keras.layers, and I will add the flatten layer here. After that I will also add dropout layer here. So tf.keras.layers.dropout, and I will give the dropout rate as 0.3, which means in every hidden layer the model will randomly switch off 30% of neurons so that it shouldn't be overfitted. And after that we will add our final output layer, which is the fifth layer for us. Let me say here output layer. Now in this output layer we will be having our final dense layer. So let me just say here tf.keras.layers.dense. Now what this output unit should be? So this will be 1. This is because the discriminator is doing a task of binary classification. It is either identifying whether the image is fake or true, which means it is performing a kind of binary classification, and hence the output unit is 1. That is, it will either generate that the image is true, or it will either generate the output as the image is false. And then we have to again specify its activation function. So here, as we are performing binary classification, we will say that the activation function that we are using is sigmoid. So this is how your discriminator will look like. And also be mindful about this input shape. This input shape attribute should only be present in the first layer and not in the remaining 2 layers. So let me just delete it. It should be present just in the first layer of the discriminator. And after doing that, we will return this model here. So let me just say return model. Now after that, we will call our model here. So let me write a variable discriminator. In this variable, I will load my discriminator model. So let me just copy the function name and I will paste it here. And let's call this function here. So after doing that, you can check the discriminator summary. You can check how this model looks like. So I will say discriminator.summary. So as you can see, this is the summary of discriminator. So we have convolutional 2D layer, then we have batch normalization layer, then we have made use of leaky ReLU function here, and the loop goes on, and at the end we have one flattening layer, one dropout layer, and the final output layer as our dense one. So after building these 2 multi-layer perceptrons, that is generator and the discriminator, now we will go ahead to define the loss functions and the optimizers. So let's write here. This is the 4th stage of the project, and that is define loss function and optimizers. Now, as these are 2 separate models, or we can say 2 separate neural networks, Hence, both will require their individual separate loss functions as well as optimizers. You cannot just define a single loss function or a single optimizer and share them between both these neural networks. It can't happen. You have to define them separately for both these models. So starting with, as you know, we are working with binary classification here. At least for the discriminator part, we will be making use of binary cross entropy here. So let me just write it first, cross entropy. And here we will say tf.keras.losses.binary cross entropy. And in this binary cross entropy, we will say from logits is equal to true. Let's run that. The E is actually small. Fine. Now we will define the discriminator loss and generator loss separately. So first here we will be defining the discriminator loss. So let me just write it, discriminator loss. This discriminator loss, this will quantify that how well the discriminator is able to distinguish between real images from fake. It will try to compare the discriminator's predictions on real images and the discriminator's prediction on fake images. And depending upon that, it will distinguish that the generated image or the image that the discriminator has received, whether it is real or whether it is fake. So let's write a function here. We will say def discriminator loss. And in this discriminator loss, we will pass two attributes. First is real output and the second is fake output. So first we will define the real loss here. So real loss is equal to, we will call this cross entropy here. And in this cross entropy, we will be passing a once array that looks like real output. So let me just say here tf.onceLike, and in this onceLike we will pass real output. So we will be creating a noise array that will look like real output here and then the actual real output. Similarly, we will create fake loss here. So fake loss is equal to, again we will call this cross entropy here. And for fake loss, we will again create an array that is similar to the dimension of fake output, but this will be a zero array. So let me just say here zeros like. So for real loss, it was once like array, and for fake loss, it is zeros like array. And here we will pass the fake output. And then again, just a minute. So here we'll again have fake output. So this was about the definition of real loss and fake loss. Then we will compute the total loss here. So let me just say here, total loss is equal to real loss plus fake loss. And after defining this total loss, then we will return this. So return total loss. So this was the function for discriminator loss. Let's run that. Now we will again define the function for generator loss, and this generator loss function will quantify that how well it was able to trick the discriminator, like how well it was produce images that the discriminator is not able to distinguish between. So let's say here generator loss and let's write a function here as def generator loss. In this function, we will just pass the fake output. Why? Because if the discriminator classifies any image as fake, that output will be passed here, and based upon that, the generator will try to improve itself. The generator will try that how good it can improve itself so that the discriminator won't be able to guess that the image was fake and not true. So we are just passing the fake output here, and then we will return the cross entropy. In this cross entropy, we will again have once like array. So once like, because the real images will be labeled as 1 and the fake images will be labeled as 0. So once like fake output, and again fake output. So basically what we are doing is we are taking the fake output label generated by the discriminator loss here, and then we are trying to improve the generator depending upon that so that the label gets converted to 1, and hence we have made use of once like here. Let's run that. So this was the function for generator loss. Now in a similar way, we again have to specify two different optimizers for both this perceptrons. So let me just say here optimizers. Now for both these perceptrons, we will make use of Adam optimizer because it's quite good and it performs really very well. So first we'll say generator optimizer, and here we will say tf.keras.optimizers.adam, and in this we have to specify the learning rate. So let me just say here learning rate is equal to, we will say 1 e raised to negative 4. You can also give it as 1 e raised to negative 5, but e raised to negative 4 would still be enough. And in similar way, we will again specify the discriminator optimizer here. So discriminator optimizer, and here again I will say tf.keras.optimizers.adam, and again we will have same learning rate here. So learning rate would remain same, that is 1 e raised to negative 4. So these are two distinct optimizers that will be provided to two different multi-layer perceptrons that we have built. Let's run that. After doing this, now we will move ahead to the main part of this project, which is defining the training loop. So let's start with that, and I will define here the fifth stage of this project, which is defining the training loop. So first we have to specify some important parameters about this training loop, the first one of which is epochs. So epochs is a kind of hyperparameter. You can play with that as well. I will give this epochs as 60. Then secondly, we have to give the noise dimension. So let's give this noise dimension as 100. Now what's the significance of this noise dimension? See, a batch of random noise is generated with a normal distribution, and the noise serves as an input to the generator. So this noise dimension defines the size of this random vector will be provided as an input to this generator. And then here we have to say number of examples to generate. This means how many images we want as our output. So let's say that we want 16 images as our output, and here we will say seed is equal to tf.random.normal, and let's pass this number of examples to generate and the noise dimension in this seed. Let's run that. Now, after doing that, here we will start writing our actual training loop. So training loop. So here I will say @tf.function. So let's write the function here, def train step, and in this we will pass the images. So images. Then I will say here noise is equal to tf.random.normal, and in this we will pass the batch size. So batch size that we have specified in the beginning of the video, and then the noise dimension. So noise dimension, the batch size is 200 here. Now after doing that, let's write the gradient here. So I will say with tf.gradient tape as generator tape, and tf.gradient tape as discriminator tape. So why we require gradient tape here? Because the gradient tape records the operations on the models during forward pass. This gradient tape basically helps us in forward pass for both the generator as well as for the discriminator. So in the forward pass of the generator model takes some random noise as an input and produces the batch of fake images. While in the discriminator forward pass, the discriminator takes that images and tries to identify whether they are fake or real. This gradient tape actually helps us to record the operations that our discriminator as well as our generator are performing during the computation process. And this computes the gradients, which later helps us in backpropagation. So let's write the code inside that. Here I will say generated images is equal to, here we will call our generator. The generator is the variable in which we have loaded our generator model function. You cannot directly pass any kind of function here. You have to pass a variable in which that function is loaded. And after that, we will pass the noise and we will say training is equal to true. After that, here we will say real output is equal to discriminator, and in this we will pass the images, and again we will say training is equal to true, and then fake output is equal to, we will again call the discriminator, and in this discriminator now we will pass the generated images. So generated images, basically this one, and then we will again say training is equal to true. As you can see, for both real output as well as for fake output, we are passing the discriminator module. This is because it is the discriminator's job to identify whether the images are fake or real, and generator is just used for generating the images. So whatever image this generator is generating are getting stored in this generated image variable, which is further passed to discriminator to identify whether the image is fake or whether it is real. And then we will here specify generator loss is equal to generator, and here we will call the generator loss function that we have specified here. So as you can see, this is your generator loss function, and the function you are calling it here. In this you will pass the fake output, and next you will specify the discriminator loss here. So discriminator loss, and here we will call the discriminator loss function. So discriminator loss, and in this we will pass both the real output as well as fake output. Now after this we will create the gradients of generator as well as the gradients of discriminator. So let me just write here gradients of generator. So here we will say generator tape dot gradient, and in this we will pass this generator loss. So let me just paste it here, and here we will say generator dot trainable variables. Similarly, we will also build the gradients of discriminator here. So let me just say here gradients of discriminator. In this we will call the discriminator tape here. So DISC tape, and in this we will again say here gradient. Here we will pass the discriminator loss, and we will say discriminator dot trainable variables. After that we will call the optimizer here. So we will say generator optimizer, and here we will say apply gradients. So let me just say here apply gradients. Then we will zip the gradients of generator and the generator trainable variables for the generator optimizer. So let me just copy this gradients of generator and paste it here, and then we have to pass this generator dot trainable variables here again in the optimizer. Secondly, we will apply this on the discriminator optimizer. So let me just say here discriminator optimizer, and here we will say again apply gradients. Here we will again zip the gradients of discriminator, and we again have to pass this discriminator dot trainable variables here. So this is where we are applying the gradients on both the generator optimizer as well as on the discriminator optimizer. So let's run this function. Now after running this function, we will write a code to generate and save images, because whatever images that are getting generated, we need to store it in order to visualize them. So let's say here generate, and just a minute, save images. Let's run that. So let's write the code for the same. Here I will say def generate and save images. This will be our function name. In this we will pass our model, then we will pass our epoch, and then we will pass the test input. So test input. Now in this function, first we will say predictions, because first we have to make predictions. So predictions is equal to model test input comma training is equal to false, because in the prediction part we don't have to perform any furthermore training. So training is equal to false. It's training and not trainings. After that, here we will say predictions again is equal to, now here we will call this initial predictions plus 1 and divided by 2.0. Now let's write the code for plotting it. So I will say figure is equal to plt.figure, and in this we will give the figure size. I will give it as 4,4. Now after that, here I will say for I in range predictions dot shape at 0. Here we will plot a subplot. So let me just say plt dot subplot, and in this we will again say 4,4 and I plus 1. After that, we will make use of IamShow method from PLT. So plt.IamShow. In this, we will again say predictions at I, and after that, we will switch off the axis. So plt.axis off, because we don't want any x-axis or y-axis to be shown. Now, after plotting this, we will save the figure, and we will save these images in the current working directory. So now, as we are working in the Kaggle working directory, all the images will get stored in the Kaggle's output directory. So as you can see here on your right hand side, so this upper portion is your input portion, and the second portion that you have here is the output portion, where you can see the path as Kaggle working. Here in this directory, the output images will get stored. So let's say here plt dot save figure, and in this we will say image. Now we want to give the names to this image, right? So we will say image at epoch. We will store every image with this names underscore 04d dot png. So this will get stored in png format. So here we are specifying 4 zeros and then the current index number, that is, let's say you are saving the first image, so it will get stored with the name as image at epoch 0001. Then let's say you are storing the 10th image, then it will get stored with the name image at epoch 0010. So we are giving 4 numbers here and it will get stored in PNG format. So let me just say here format epoch. So whatever the epoch number is, with that name the image will get stored. After that we will close it. So plt.close. Let's run that. Now let's write the final training code. So let me just say here def train, and in this train we will pass the dataset and the epochs. So here we will say for epoch in range of epochs print. So as the code is running, we want to print the current status of model. So we will print as starting epoch, then epoch plus 1, because it will basically start with 0 and we want to start with 1, hence epoch plus 1 out of epochs. So this epochs will have the total count of epochs that we have specified, which is 60, and the first epoch plus 1 will specify that right now we are at what epoch. So let's say we are currently at second epoch, it will specify second out of 60. So this is the status that will be displayed on screen after every epoch. Now after that, here we will say for image batch in dataset train step. So here, as you can see, now we are calling this train step function. So whatever function we wrote here of train step, that we are calling it here in the final training function. And here we will pass our image batch. Now this dataset will hold our TensorFlow dataset. As you know, in the beginning of this video, we have generated a batch dataset. So as you can see, this train data set, this is your batch data set, and that will be passed here to the train module, out of which every image batch, so every image batch is of 200 images, and that will be passed to this train step function. Now coming out of this for loop, here we will call this generate and save images function. So let me just call it, and after calling this function we have to pass the arguments. So first we have to pass the model, which is generator. Then we have to pass the epoch, so let me just say epoch plus 1 because we have to start from 1, and then seed. Again, be mindful about passing only the generator variable here and not the function. So let's run this function. Now after that, let's call this function, which will be the final step of this project. So let me just call this function train, and in this we have to pass the data set. Let me also give the heading here as training the model. Now in this train we have to pass two arguments, which is dataset and the number of epochs. So the dataset is nothing but the train dataset, as I already shown you, that is your Tensorflow batch. And then you have to specify the number of epochs that you have specified. So as you can see here, you have specified the number of epochs as 60, and that you are passing it here, and then here you are passing the train dataset, which is the Tensorflow batch dataset that you have generated. So let's run this. So as you can see, the epoch has started, and currently we are at the first epoch out of 60, and as soon as this image will get generated, it will get stored here in the output. Right now this Kaggle working is empty, and as you can see here, we also have table of contents. So in this project, what all steps that we performed, they are listed here. And as you can see, we went on second epoch, which means the generation of first image is successful. So in this Kaggle working, now we might have our first image. So let me just open it. And as you can see, this image at epoch 1110 is now generated in PNG format. We cannot view it here in the Kaggle environment, but we can download it. So once you click on the three dots, you get this download option. And when you click this download, the image will get stored in your system. So this training will now take a lot of time. It will take around 1 hour, or might take 1.5 hours. So the training now has been completed, and as you can see, at the end of 60th epoch, we get all these images stored in the Kaggle working directory. And this took me around 2 hours to complete. So now let's try to display some random 3 images from this entire directory. So let's say here, visualizing the images, any 3. Now for this we require random module, so let me import that first. So here I will say import random. Let's run that. Now coming back to this visualizing cell, here first I will give the image folder in which we have all this images stored. So image folder, and we will just copy the path of this Kaggle working from here and paste it here. After that, we have to get a list of all these images from this directory. So here I will say image paths. So here I will say os.path.join. So we are joining this image folder, which will be the base directory for this visualization purpose, with file, for file in os.list directory of image folder. So one by one we will extract all the images from this image folder, and then we will append it to the base directory to access the image. And we also have to give one condition here, and that is if file dot ends with PNG. That is, we are saying that we only want the images that have an extension of PNG. Now we know that we already have all the images in PNG format. Still we will do that, because by chance if we get any corrupt file in this, still we will only try to get the PNG files. After that we will select any 3 random images. So let me just say here random images is equal to, I will make use of the random module that I have imported, dot sample, and here I will pass this image path, and I also have to specify how many random images I want. So here I will say 3. Now coming down, I will create a subplot. So figure, comma axis, plt.subplots, and in this we will pass 1, 3, which is 1 row, and in 1 row we want 3 columns. Then we have to again give figure size, Let's keep it as 15,5. And after that, coming down, let's write a for loop here. So for axis, comma image path in zip axis, comma random images. Here I will say image is equal to image. This is the module that we have imported from PIL library, and we will make use of that to open the images with the help of path. So here I will provide this image path, and then we will switch off the axis, and then we will display it using the IAMShow method, and here we will pass the image. Now we will also switch off the axis because we don't want any x-axis or y-axis to be shown. So here I will say off, and let's run that. So as you can see, these are the images that we have got. The first two seems like they were in the initial process of reconstruction, and the last one seems quite a constructed image because you can still analyze some human faces from this. Let me just zoom it, and as you can see, the initial process of construction consists a lot of noise, while the end one consists a bit less. So here you can spot quite a few faces of humans. I know that this isn't very high resolution images, it consists of a lot of noise, but this is again because we have used 64 by 64 as image size. If you see our original images, even they were quite a blur, as you can see. So if you want very high resolution images as output and very clear ones, you have to work with 256 by 256. But the kind of thing that we have generated out of this highly blurred images is still very powerful. So you can find some faces here, and let me just run it some more times to get more random images here. So even here you can see, you can find some human faces here. So this is the human face reconstruction that we made, and I will also attach a small video clip that shows the evolution, or we can say transition, from the first image up till the 60th epoch, so that you can compare and conclude that how good the transition have happened. And I will also provide this code. So I have this GitHub file in which I have written all the theoretical part along with the important concepts that you can just understand after looking at this file. And here we even have the output attached. So I will link this GitHub repository in the description box. Do check that. And I forgot to mention one point in the beginning of the video, and that was this DCGAN, the Deep Convolution Generative Adversarial Network. This is a kind of unsupervised learning in deep learning. Like we have supervised and unsupervised learning in machine learning. Similarly, we also have this in deep learning. But till now, all the work was done on the supervised part of the deep learning. This GAN is a kind of unsupervised learning field that we are exploring in deep learning. Because you might have noticed that here we don't have any target data. This is just the input data of images. We don't have any targets to compare it with. So this is a kind of unsupervised learning that we are performing in deep learning. So that's it for the video. Thanks for watching.